So I'll talk about kind of the ordinal optimization and then beyond how I kind of came up with the idea of the OCBA that Liu just mentioned, and then also some of the new search we are heading for. First of all, again, I want to echo with many presenters today. I really greatly appreciate Professor Hall. Actually, I did not plan to do a PhD at all at the beginning. So without Professor Hall, I would not have stand here. Thank Professor Hall for the opportunity coming to the US and then get a PhD degree. So I came in 1991. Actually, so I have 1 year overlapping with Liu Yan. That's really was an excellent time, so enjoyable. And actually, I was the 39.
Yes,
yes. I was Professor 39, so my number is 39. And appreciate Professor. It's more than just doing research. Professor always share his wisdom in terms of the life with us. So I still remember one story. In one of the party, Professor Hall told a student, including me, that you should give people more credit. And I still remember at that time my English was so poor. I asked Professor, what do you mean by give people more credit? Because my English was poor, I was thinking about credit means credit card. So I still remember. So I asked Professor, what do you mean by how can I give people more credit cards? But luckily, Professor can speak Chinese, so he used Chinese to explain to me what does he mean by credit. But it's really useful and very, very helpful. So a lot of advice from Professor Hall. Thank you very much. So before I talk to that, I also want to talk about a little bit because yesterday a lot of people struggle with the flight delays. I believe I was one of the group, number one coming to after the landing. But yeah, so we talk about a real-time application. I did several projects with NASA and FAA. So my original flight was canceled. But then I think we chose a good flight to come in time. So just share a little bit with you some of the experience we learned from the FAA and NASA projects. I think the situation in China now is that the lambda is much bigger than mu. We talk about queuing theory, right? So now the lambda is bigger than mu. So that's the problem. That's the problem. We cannot change the mu now. But this is kind of my suggestion in case next time you have a similar situation. So the way I choose since lambda bigger than mu, so the queue is going to build up very quickly. So yesterday when I rebooked my flight, the one I chose is that first of all I need to look at the weather and then see when the typhoon is leaving. So I need to book a flight which arrives right after the leaving, a little bit after the leaving. So then if the queue is going to be long, what do? I need to jump ahead of the queue and then try to get in as quick as possible. So I need to arrive before the queue starts to build up. The other suggestion is that you should avoid short flight because when they do the flight control, usually this is a rule, the longer flight has higher priority. So if you tend to have a shorter flight, one of your leg is short, that one is very unreliable because that one always has a low priority whenever there is something happening, which is something, the control, they call it ground delay program. So basically they delay the flight based on the distance. The shorter distance is lower priority. The other one is that you avoid the congested area. When the flight, before the takeoff, they need to make sure the whole flight path has enough capacity. So even you have a little bit portion going through a congested area, your flight cannot take off. So that's for example, the Shanghai area. If you go to Shanghai, you have better take high-speed train because that is a congested area. Well, we're talking about can we increase the mu? We know the queuing theory. Can we increase the mu? The problem is in US, the separation standard is about 45 seconds between two flights. But in China, they put 2 minutes to increase the mu. We did the safety analysis. In US, when we did the safety analysis, US put the standard as the 10 to minus 9. But I heard that in China, they don't want 10 to minus 9, they want 0. So, so that's why they cannot increase the mu too much. They don't want to increase the mu. They don't want to put the airplane too close. So in US, you can see that two airplanes can land almost side by side. I don't believe that can happen in China. You can see that this is the tip. This could happen in US, two side by side. But I don't think in China they are going to take that kind of risk. Well, okay. So I get back to my since I know many of you struggle with the flight yesterday, so I kind of insert two slides to do. But I'm very glad to see you, and particularly I thank Professor Yao organizing this, and then I saw he communicate with everybody, and then we're glad to see so many people. So, well, I think that Professor Ho and several people talk about this this morning, from the continuous control to the perturbation analysis. But I didn't do the research on that. Actually, I'm on the third part. So the reason I put which year I came to Harvard is that I still remember 1 year before me came to Harvard. That's 1990. I'm not sure Professor still remember. From 1990, you switch all your new students from 1990 to
91. 91 is when I first got inspiration for auto optimization, yeah.
Well, but I came in 91, and then all the students 1 year before me started ordinal optimization. Or maybe they were taking classes. Maybe they were.
Sure?
Yeah, I'm sure.
I'm very sure 1991 was the first idea.
Because I came in 91, and I know all the students. Yeah. Anyway, so that's the Professor Ho started the ordinal optimization, and that's how I got into this area. So I didn't do the research on perturbation analysis. So I see that as a very fast solution for the hard optimization problem, which is very important for the, right now we talk about big data. I think it's very important. I want to use now everybody talk about big data. I see that the data is more than just data. It's kind of integrated system. So the system get bigger and more complicated. Talk about IoT, Internet Plus, Industrial 4.0. In US, we call it cyber-physical system. Pretty much, I think the similar is the kind of integrated system, very, very big system. And in this kind of the new era is the connection and integration. So system gets bigger and bigger. And we have more sensors, we have more information, we have more factors to include in our decision making. And then the data keep coming. So we have even actually, the problem gets bigger, gets more complicated, but we have less time to make a decision. And further, people want to make a smarter decision. Everything must be smart. So I think that kind of echo with the Professor Ho's inspiration on solving the hard problem in a very quick way. Is that problems are getting bigger. We need a large-scale optimization. We need a simulation in order to deal with the complex problem. We also need efficiency. So I see that I really appreciate Professor's wisdom that even well before the big data era, and then come up with the kind of a start to moving toward that direction. So in my research, I would say put that into this framework so-called simulation optimization, which I think Loyan just introduced that we want to use simulation to evaluate the system, and then eventually we still want to optimize the system. The two main challenges, if I to simplify that, is one, first of all, stochastic simulation to do the multiple replications. Secondly, for the optimization, I have multiple alternatives to simulate. So which kind of make the computation time very challenging. So if I put a simple graphics to illustrate idea is that this is the number of simulation replications that in order to get estimate, I need to do multiple replication. But for the optimization, I need to do the multiple designs. So the total simulation cost could be very expensive, as Loyan said that for the real-time decision problem, I want to reduce the computation times. So that's I kind of learned from the ordinal optimization. We want to make it quick. So our professor come up with the idea. First of all, we want to focus on good enough decision. We want to focus on good enough solution. So then we can reduce the computation time to a much smaller, a small rectangle. We don't need to simulate that many designs. The number of designs we need to simulate can be much smaller. I'll further explain to that in the next slide. And then if I focus on the relative order comparison, then I don't need to run so many replications. And then OCBA, I think this is when I did a PhD student, I see, well, based on this, we can further improve the efficiency. So with the OO, the computation effort is a big rectangle. With OO, we can reduce to the small rectangle. But the OCBA says that, well, we don't need to equally simulate them. If I can control the simulation in a smarter way, then I can further reduce the computation time to that shaded area, which is kind of motivated by OO, but we want to further enhance the efficiency. And recently, we kind of moved toward a new direction called Ordinal Transformation, which I'll introduce that to you at the end of my talk. So first of all, ordinal optimization, focus on good enough decision. We can do a much, it can reduce the number of design you need to simulate in a much, much smaller number. I think a lot of people have worked on that. Second one, the advantage of OO is that the simulation accuracy can be enhanced by at the rate of 1 over square root n. But if you focus on the order, there are some papers showing that actually the convergence rate is exponential. I think Professor Ho has a very nice website showing the advantage of that. Now, after the OO, as I said, the OO advantage, you can reduce a hard problem into a much smaller problem, much smaller number of the computation efforts. Inspired by that, actually, is a big problem to a smaller problem, and it happened to be this so-called ranking and selection problem in the simulation society. So that's how, after I graduated, I realized, well, some people has worked on that. It's called ranking and selection problem, but it's interesting. Actually, it turns out it's very interesting that the ranking and selection problem they have worked on at the time I graduated, they have worked on for about 20 years. And then most of the result, they work on that, they say, hey, if you look at a small problem and only look at the order, and then how you control the simulation, they come to a conclusion saying that you should control your simulation in the effort that are roughly proportional to your variability of your estimate for that particular design. In theory speaking, it makes sense. If you have higher variability, you want to put more effort. So instead of equally simulating all the alternatives, you want to put effort on the design which has higher variability. But I guess I'm coming from the different background, from the different training of Professor Hall. I raised the question, if you look at this example, if I find alternatives for minimizations, if this is the preliminary simulation, you found this is the confidence interval based on your estimations. You say, hey, 2 and 3 are much better than 1, 4, 5. But 1, 4, 5, design 1, 4, 5 has much higher variability. So when I just came to this society, a lot of people are still talking about you should do, if you find out you want to find optimal designs, where you should put your extra computational effort. And then a lot of people are still talking about putting on the 1, 4, 5. But I said, wait a second, because we know 1, 4, 5 is much worse. You should kind of concentrate on the 2 and 3. So that kind of motivated. It says that we have a lot of room to improve that. So furthermore, I kind of formulate the problem as an optimization problem. How we control the simulation? In order to find the best alternative design among a set of the alternatives. And so I formulate as an optimization problem. And by making some assumption, by making some simplification, we derive some nice result. We call it OCBA, Optimal Computing Budget Allocation. So the goal is I'm hoping to maximize the efficiency for simulating a set of the alternatives. And the results actually are pretty simple. Let me use this simple example to explain the ideas. That if you look at the design 2 and design 3, suppose I have a 3 design and then say 1 better than 2 and 3. How do I control my simulation? The allocation between 2 and 3 should be in the way that if you look at this, it's inverse proportional to this number. So delta is the difference. Delta is the difference from the best. So it's like if you are away from the best, you shouldn't allocate too much. On the other hand, it's proportional to your variability. So on the one hand, it's similar to what traditional researcher has shown. But on the other hand, we show that you need to consider another factor, which is also important. in the so-called optimal allocation. So put it a simple word is that if I define the delta over sigma as so-called signal to noise ratio, then the allocation should be inverse proportional to the signal to noise ratio. I think Leyen mentioned that. So this is a so-called we developed a version of the OCBA, but these are based on some simple setting. So a lot of research, we make a lot of assumptions, a lot of observation at the beginning, but I think it's interesting that a lot of researcher has the kind of the generalized or even extend to the more general setting, including tomorrow's speaker, Lucy Powell. He has a kind of extend talk about how you control the simulation to minimize the variability of the design. So we work on several of you, including, actually I work with Leyen, Shi-Yang, and several of you, and I think we still, a lot of research continue on that. So I'll leave some more research for the next two talks. And we have a book on that. And so I want to move to the, I want to leave the OCBA. I think that's we're pretty exciting. Although at the very beginning, we really have a hard time when I just graduated, and when I told them, hey, your simulation was not totally right? Actually, the people say, you are too crazy. This is a crazy guy. So by that, I want to encourage those young people. When people say you are crazy, actually, you should continue working on that. Now, I kind of I want to move to the next topic is that I want to continue to improve the efficiency. So I guess my research is always I want to improve the efficiency. So by using the OO or the OCBA, well, I'm still not totally happy. We want to make it further faster. So the next subject I want to talk about is if I have some simplified model, some approximation model, which are much faster than simulation, can I utilize those approximation models to enhance my efficiency of finding the optimal? I'm sure, for example, like simulation, instead of doing simulation, can I do the queuing theory? Queuing theory is much faster, but probably poor approximation. Can we do that? That's the kind of the starting idea. Again, my purpose, I want to utilize that to help me to find the optimal design. Another one is the coming idea of the big data. The data keep coming, keep changing. But before the new data come in, I might have using the oldest data to run simulation. Can I use the result from the simulation using older data to help me to make a better decision for the new data? Again, my goal is that I want to enhance my computational efficiency. So that is the goal. I'm hoping to use the approximation model or the older data results, and then to help me to find the optimal design. So I want to use this simple example to illustrate the ideas. Say I have this is the optimization problem, this resource allocation problem. Say I have two products sharing this flexible manufacturing plan. Two types of product, and now I have some finite resource I want to allocate to these 5 workstations. So this is a cooked up example. Say I have some machine I want to resource I want to allocate this 5 workstations. So I have a 780 alternative. So if I run the simulation, this is still doable. I run the simulation, so I want to compare this. We can run simulation, or you can do the queuing theory. So I show this horizontal horizon is this 780 alternatives, possible allocation of my resource. And then the y-axis is the estimation, either from simulation or from the queuing theory. So as you can see that the estimation of queuing theory is very poor. It's very poor. The red line is from the simulation we consider as the accurate result. The blue line is from the queuing approximation. The approximation is very poor. So the question is, those poor approximation, are those poor approximations useful to help me to enhance the efficiency? So again, motivated by Professor Hall's OO, ordinal optimization, we propose an idea we call ordinal transformation. So idea is as follows. Even though the approximation is very poor, their order actually is somehow useful. Their order is somehow useful. So instead of putting the original domain space, I use the order of my approximation. Remember, the approximation is very quick. I can easily do the calculation. I use that as my coordinate transformation. I transform into a new space. The new space is the order of the simplified model. And of course, the queuing theory, because it's based on the queuing theory to the queuing approximation to do that, so it's a monotonically increasing function. But I want to use this example to show what is the result we get. You can see that, hey, if I do the transform to the new space, you will see that in the original space, the response could be very, very bumpy. But after I change to the new space, we get some nice properties. What kind of nice property we got? The non-smooth response can become much smoother. And the neighborhood connection can be strengthened, which is good because when a lot of search methods require some neighborhood structure or at least neighborhood connections. So by doing the ordinal transformation, we can enhance that kind of connection so that can help some of the search or optimization efficiency. Mathematically, we have proved something that indeed that we can bring some benefit. Of course, the benefit depends on how good your approximation is. In theory speaking, if you have a good approximation, of course, you bring more benefit. And we use the rho, which is the correlation. At this point, we use the rho, which is the correlation between the real model and the approximation model. In theory speaking, if you have a higher correlation, we can bring more benefit. This is the result showing that indeed this method can significantly enhance the optimality of the result we can search. Now, I want to show the example. How do we use the data, the order data? Say I want to use the modified data, so the same thing. The one I just say, in that problem, if the product is 250, 150, the flexible manufacturing example, there are two products. And the example I just showed, if I can use the queuing approximation, we got pretty nice result. Can I use the order data? Can I use the order data? I want to show you an example. Can I use the two set of order data? Remember, this is the one I want to simulate. 250, demand is 250 and 150. If I have to go back to my database, I found I have two sets of data. One is 210, 170. The other set is the 280 and 140. These are order data. Suppose I already have the simulation. Can I utilize the simulation result to help me find the optimal design for my new demand, for my new problem? So actually, to some extent, I'm using two simplified model. To help me to find the optimal design. So the two, so this kind of joint work with the Si Zhang. You are the next speaker, right? So we find a way that how do I combine? If I have a two approximation model, how do I combine two approximation model? Each approximation model has their order. So the way she proposed is that I do a linear combination. We do a linear combination. But when I do the linear combination, I want to maximize the correlation between the combined model and the true model. We derive some of the optimal results. So I want to quickly show the results. If I combine two models, if I only use a single model, the rank correlation, look at the top 5 and look at the overall correlation. The single model is only give you like around 0.6 correlation. But if I combine two models, of course you need to carefully choose these two models. Otherwise, if two models are identical, the second model doesn't help. But if you carefully choose your two models, the one I just showed you, actually it turns out that if you choose two models, I can enhance the correlation to 0.875. If you look at the alignment, look at the alignment of the top 5 design. If you only use a single model, it's only show you 2 out of the 5. But if you combine the two models, if you choose the two models in a nice way, we can come up with the 5. The alignment can increase to 5. So more carefully look at in what case the second model can help you, or in what case, in what situation the second model will help you. So suppose your first model has the correlation 0.6 with the true model, and the different color means the correlation between the combined model and the true model. We want that as high as possible, which is the red color. So we prefer this area. So that means if my second model, say I choose the second model also 0.6. So where can I bring the best benefit? Is this area, right? I want the red area. So that means what? The second, you had better choose the second model in a way that it will row 1, 2, which is the correlation between the first approximation and second approximation model, around, actually it's a negative correlation. So intuitively speaking, that makes sense. If you want the two approximation model to help you, you have better these two approximation model are kind of somehow negatively correlated, which kind of provide you the different information. And we are, I think that intuitively speaking, that makes sense. And of course, in general, how do you always choose the two negative correlated approximation model? So that require more research. In summary, I kind of first of all I introduced the ordinal optimization, which inspired me on my research, and I briefly talk about the OCBA, which kind of to enhance by controlling the simulation budget allocation to enhance the simulation efficiency. I know there are next two talks are related to this, and also briefly talk about ordinal transformation, which use the order of the approximation model to change the design space into a new space where it's make the space easier to search, and which kind of help to enhance the efficiency. Once again, I want to thank Professor Hall very, very much. That really changed. He really changed my life. Thank you very much, and thank everybody.
Thanks for Chen's talk, which gave a very quick and understanding of your research during the past years. So any questions? Okay.
Yeah, this may be something that we can take offline.
Okay.
But as we were talking, because I hadn't really thought too much about this in recent years, in the spirit of big data,
Yes.
it seems to me that there might be an inverse problem here, in which case I don't want to really think about simulation. I want to think about more data from our multiple sensors that are out there. So the issue of where is it more beneficial as data are coming in to focus on, like this sensor is giving me more data than that sensor. So it seems to me that there might be, in the same elegant framework that we're trying to build, an inverse problem to solve this, which might be more sexy.
Yes.
Interesting.
Yes.
As we move forward, because that's where the real beef is.
Yes.
The data.
I totally
I mean, much as I'm with you as far as simulation goes, and we all love simulation and all that, I think that in the future we won't really be doing simulation as much as processing data.
Yes.
So maybe we can take it offline. But this is just
I kind of feel both. I totally agree. I totally agree with you. I think inverse is important. But I still feel that simulation is important if you want an unbiased estimation. And or you want to simulate some kind of what if, where data cannot tell you. Sometimes if data cannot tell you, then what do you do? Like AlphaGo, right? We know AlphaGo, it sounds very fancy. They beat the human. But if I change the rule of the Go, say I change the game, I don't believe that they will play well. Right, because they have a trend, they have learning. So I think we come to the professor's automation problem, right? If everything, all the world doesn't change, then I guess computer does very well now. But I think simulation at some point still require. Otherwise, if the rule change, I don't believe data can 100% tell everybody. But I agree with you. Data can say that.
They're different problems, but under the same framework. Instead of thinking of how much time I should be spending, I'm thinking about how much data I should be collecting from this source as opposed to that source. So I'm just trying to transform what you're doing into a different settings, which might be the future.
Sure, I agree. Good, thank you.
Okay, I think Professor Xia from Tsinghua University.
Yes.
Sure.
So your OCBA give us a guideline how to allocate the simulation. You have the formula similar to the signal noise ratio is very elegant. But in Jeff Hong's talk, he mentioned the much more
Yes.
problem. It is also about how you allocate your budget, your money among different different bandits. So they also have some formula like UCB formula.
Yes.
Average of your performance plus something like a square root, something like this. So how is the relation? I think that these two problems is very similar. And
I think the settings are very different. Multi-arm-banded problem, they care, because every time when you play, you care about you get some reward.
yeah.
So either you want to minimize the regret, or you want to maximize the total reward you collect. OCBA is I care about, I choose the optimal decision. So let me give you an example. Say your optimal decision, your best design. For example, if your best design has 0 variability, OCBA will say you don't need to simulate too much on that one, because you're already very sure about that design. But UCB is that every time when you play, you want to play the machine which is the best. You want to collect as much as possible.
Very similar. You see, in the UCP, you have a mean performance plus a square. A square, there is the number is related to the number that you have played. So according to the central limit theory, if you play this arm more, the variance will be reduced.
Yes, but again, asymptotically, there may be some relationship. I agree, asymptotically. But yeah.
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 I believe there are lots of in common, but also some difference. And I think due to time limitation, maybe I have to stop the discussion here, and we can have more discussion offline. Sorry about. Okay, thank you.
Thank you.